Welcome to this problem walkthrough. Today, we'll explore problem number 1093, titled Statistics from a Large Sample. In this problem, we'll break down how to compute essential statistical measures such as minimum, maximum, mean, median, and mode from a dataset. Let's dive in and tackle this step by step. In this problem, we are tasked with analyzing a large dataset represented as an array called count. Each index I in this array corresponds to the integer I, and the value at that index, count I, tells us how many times I appears in the dataset. Importantly, the entire dataset has exactly some count elements, meaning the sum of all the values in the count array gives us the total number of integers in the dataset. Our goal is to calculate 5 different statistics from this dataset. First, the minimum, which is the smallest integer present. Second, the maximum, which is the largest integer. Third, the mean, which is the average of all integers in the dataset, calculated by dividing the sum of all elements by the total number of elements. Fourth, the median, which is the middle value when the dataset is sorted. If the total number of elements is even, the median is the average of the two middle values. Lastly, the mode, which is the integer that appears most frequently in the dataset. If there are multiple modes, we will return the smallest one. The result will be an array containing these values in the order minimum, maximum, mean, median, mode. While the minimum and maximum will be integers, the mean and median need to be floating point numbers rounded to 5 decimal places, and the mode will also be an integer. Let's now look at an example to better understand this problem. Suppose the input array count is defined as 0, 1, 3, 4, 0, 0, 0, 0, where most values are 0 except for a few. This means that the dataset contains integers based on these non-zero counts, 1 occurrence of 1, 3 occurrences of 2, and 4 occurrences of 3. If we write out the dataset, it would look like 1, 2, 2, 2, 3, 3, 3, 3. From this, we can identify the statistics. The minimum value is the smallest number, which is 1. The maximum value is the largest number, which is 3. The mean is calculated by taking the sum of all numbers, which is 20, and dividing it by the total number of elements, 8, resulting in 2.375. This value is rounded to 5 decimal places. Next, we calculate the median. Since the dataset has an even number of elements, the median is the average of the two middle values. Here, the middle values are 2 and 3, so the median becomes 2 plus 3, / 2, which equals 2.5. Finally, the mode is determined by finding the most frequently occurring value. In this case, 3 appears 4 times, which is more than any other number. Therefore, the mode is 3. The output for this example is the array 1, 3, 2.37500, 2.50000, 3, representing the minimum, maximum, mean, median, and mode, respectively. Moving on to another example, let's consider count equals 0, 0, 0, 1, 0, 0, 1, 0. This dataset contains just two numbers, one occurrence of 3 and one occurrence of 6. From this, we can identify the statistics. The minimum value is 3, and the maximum value is 6. The mean is calculated as the sum of the values, 9, divided by the total count, 2, giving us 4.5. Since there are only two elements, the median is the average of the two values, which is also 3 plus 6, / 2 equals 4.5. For the mode, since both numbers appear only once, we return the smallest one, which is 3. The output for this example is 3, 6, 4.50000, 4.50000, 3. Finally, it's important to consider the constraints and edge cases. The array count always has a fixed size of 256, and each value in count can range from 0 to 10⁻⁹. The total number of elements in the dataset, sum, count, will always be at least 1 and at most 10⁻⁹. Special cases include datasets with only one unique value, where all statistics will simply equal that value, and datasets with an even number of elements, requiring careful computation of the median. Efficient computation is critical here, as the dataset can be extremely large, making it impractical to explicitly construct the dataset. Additionally, numerical precision is important for the mean and median, as these must be rounded to 5 decimal places in the final result. When tackling this problem, one straightforward approach we can consider is the brute force method. The idea here is to reconstruct the dataset explicitly based on the count array. Each index in the count array represents a value, and the value at that index tells us how many times it occurs. By iterating through the array and generating these values according to their frequencies, we can rebuild the dataset and then calculate the required statistics, such as the minimum, maximum, mean, median, and mode. While this approach might seem intuitive, it comes with significant trade-offs. First, reconstructing the dataset requires both time and memory proportional to the size of the data represented by the count array. Additionally, calculating the median would require sorting the reconstructed dataset, which adds further computational overhead. While this method is simple and easy to implement, it is not efficient for large datasets due to its high memory usage and slower runtime, making it impractical for this problem. A more efficient solution is the optimized approach, which avoids the inefficiencies of dataset reconstruction. Instead of rebuilding the dataset, we calculate the required statistics directly from the count array. Since each index in the array corresponds to a specific value and its frequency, we can extract the statistics by iterating through the array once. For example, the minimum can be determined by finding the first non-zero index, and the maximum is the last non-zero index. The mean is calculated using a weighted sum formula, dividing the sum of values weighted by their frequencies by the total count of elements. The median can be found by tracking cumulative frequencies and locating the middle value or values, depending on the total count being odd or even. Finally, the mode is simply the index with the highest frequency. This approach leverages the count array structure to compute all statistics efficiently, avoiding the need for sorting or additional memory. While this method is significantly faster and more memory efficient, it does require careful handling of edge cases, such as empty datasets or when the total count is even. The optimized approach is the clear choice for this problem because of its superior efficiency in both time and space. By relying on the structure of the count array, we avoid the overhead of dataset reconstruction and achieve a linear runtime, processing the array in a single pass. This method is particularly well suited for large datasets, as it minimizes memory usage and handles all edge cases effectively. For instance, calculating the median directly from cumulative frequencies avoids the need for sorting, which would have been computationally expensive. When comparing the two approaches, the brute force method is slower and more memory intensive, requiring space proportional to the reconstructed dataset and additional time for sorting. On the other hand, the optimized approach achieves constant space complexity and linear time complexity, making it ideal for scaling to large inputs. By balancing efficiency and simplicity, this approach meets the problem's requirements while eliminating unnecessary computational overhead, making it the most practical and robust solution available. To tackle this problem, we need to compute 5 statistical measures: the minimum, maximum, mean, median, and mode from a dataset represented by a count array. This array is structured so that each index represents a value, and the value at that index indicates how many times the number appears in the dataset. For instance, if count 2 equals 3, it means the number 2 appears 3 times. The dataset values range from 0 to 255, so the array has a size of 256. To begin, we extract essential information from this count array. This means identifying all non-zero elements to figure out which values are present, calculating the total frequency of elements, and determining the total sum of values using the formula I*count, I, for all indices I. This summary information will serve as the foundation for the rest of the computations. The next step involves determining the minimum and maximum values in the dataset. The minimum corresponds to the smallest index I where the frequency count, I, is greater than 0. Conversely, the maximum is the largest index I with a non-zero frequency. This is achieved by traversing the count array, starting from the beginning to find the minimum, and from the end to find the maximum. After that, we calculate the mean of the dataset. The mean is simply the total sum of all values divided by the total frequency. To compute this, we calculate the weighted sum of values using the formula total_sum equals sum, I*count, I, for I in range, 256, and the total frequency is sum, count. Dividing these two gives the mean, which provides the average value in the dataset. Now, let's calculate the median, which represents the middle value of the dataset. If the total frequency is odd, the median is the single middle value, and if it's even, it's the average of the two middle values. To find it, we use the cumulative frequency approach. As we iterate over the count array, we keep a running total of frequencies. The median corresponds to the index where this cumulative sum crosses the middle point of the dataset. In cases where the total frequency is even, we'll need to identify the two indices around the middle and compute their average. After the median, we determine the mode, which is the value that appears most frequently. This is done by traversing the count array and tracking the index corresponding to the maximum frequency encountered. Both these calculations ensure we accurately capture the central tendency and the most common value in the dataset. The key insight here is the efficiency of working directly with the count array rather than reconstructing the dataset explicitly, which would be computationally expensive. For example, using cumulative frequency to calculate the median allows us to avoid sorting or explicitly creating the dataset, which significantly optimizes the algorithm. Similarly, calculating the mode in a single pass ensures minimal space usage. The data structures used include the count array to store frequencies, a cumulative frequency variable for efficient median calculation, and a few variables to hold intermediate results like the total sum, total frequency, and the statistical measures themselves. The time complexity of the algorithm is 256, since we traverse the count array a fixed number of times, and the space complexity is 1, because we only use a constant amount of additional space. Finally, let's address some important edge cases. If the dataset is empty, meaning all values in the count array are 0, the total frequency will also be 0, and we should return placeholders like none for all the statistics. For a dataset with only one value, where only one index in the count array has a non-zero frequency, all the statistics, minimum, maximum, mean, median, and mode, will be the same and equal to that single value. Lastly, for datasets with very large frequencies, it's crucial to handle integer overflow by ensuring we use data types that support large values. Accounting for these edge cases ensures the robustness and reliability of our solution across various scenarios. Here, we start by defining a class named solution and a method called samplestats that takes the count array as input. This array represents the frequency of each integer value from 0 to 255. First, we calculate the total number of elements in the dataset, denoted by n, by summing up all the values in the count array. Next, we initialize variables to track the minimum and maximum values, which will represent the smallest and largest numbers observed in the dataset. Additionally, we initialize total_sum to help compute the mean, and mode to store the number with the highest frequency. The variable max_frequency helps us keep track of the largest count observed so far. Now, we loop through all 256 possible values. For each value, if its count is greater than 0, we check if the minimum has already been set. If not, we assign the current value as the minimum since it's the first non-zero count. The maximum gets updated to the current value each time we encounter a non-zero count, ensuring it holds the last valid number. Meanwhile, we add the product of the current value and its count to total_sum to assist in calculating the mean. To find the mode, we compare the current count with max_frequency and update both max_frequency and mode if the current count is higher. Finally, we compute the mean by dividing total_sum by n. At this point, we also prepare to calculate the median by initializing cumulative_count and median, along with a list median_positions to determine the relevant positions for the median based on whether the dataset size is odd or even. If the dataset size is odd, we set median_positions to contain just one value, which represents the middle position. For an even dataset size, we include two positions corresponding to the two middle values. Next, we begin another loop through all 256 values, using cumulative_count to track the running total of counts as we progress. For each value with a non-zero count, we add its count to cumulative_count. While there are still positions left in median_positions and cumulative_count is greater than or equal to the next median position, we determine the median. If median has not been set yet, we assign the current value to it. Otherwise, since we're dealing with an even dataset, we calculate the average of the two middle values. Once a position in median_positions is processed, we remove it. Finally, after completing all calculations, the function returns a list containing the minimum, maximum, mean, median, and mode, all converted to floating point numbers for consistency. This concludes the implementation of the function to calculate these statistical measures from the given dataset. Here, we begin our Java implementation by defining the sample_stats method, which takes an integer array count as input. This array represents the frequency of each value in the sample, where the index corresponds to the value itself. We initialize several variables: total elements to track the total number of elements in the sample, total sum to calculate the cumulative sum of all values, and minimum and maximum to store the smallest and largest values with non-zero counts. We also initialize mode and max frequency to identify the value with the highest frequency. Next, we iterate over the count array. For each non-zero count, we update the minimum if it hasn't been set yet, and adjust maximum to reflect the current index. The total sum is updated by multiplying the value at the current index by its frequency, and total elements is incremented by the count at that index. Additionally, if the current frequency exceeds max frequency, we update mode to the current index and max frequency to the new highest frequency. Finally, we calculate the mean by dividing total sum by total elements. Now, we calculate the median, which requires determining the middle value or values in the sorted sample. We initialize median to 0.0 and calculate two positions: median position 1, which represents the first middle position, and median position 2, which accounts for the second middle position if the total number of elements is even. The positions help us determine which values contribute to the median. We then iterate through the count array again, keeping a running total of cumulative count. When this cumulative count reaches or exceeds median position 1, we add the current index to median as the first median value. If cumulative count reaches median position 2, we add the current index again and take the average if both positions are needed. This ensures that the median is calculated correctly for both odd and even total element counts. Finally, we return a double array containing the minimum, maximum, mean, median, and mode values in order. To begin, we have a simple dataset represented by the count array. It contains the frequency of elements from 0 to 255, but only positions 2 to 5 have non-zero values. First, we calculate the total number of elements, n, which is the sum of all frequencies. 1 plus 2 plus 1 equals 4. Next, we initialize variables for our statistics. Minimum and maximum will track the smallest and largest elements, total_sum will accumulate the weighted sum of all elements, mode will hold the most frequent value, and max_frequency will help determine the mode. Now, we iterate through the array. At index 2, the frequency is 1, so we set minimum and maximum to 2, as it's the first non-zero value. We update the total_sum by adding 2 times its frequency, resulting in 2. The mode is updated to 2 since it has the highest frequency so far. At index 3, the frequency is 2, so we adjust the maximum to 3 and add 3 times 2 to the total_sum, making it 8. The mode is updated to 3 because its frequency of 2 exceeds the previous maximum frequency. Finally, at index 5, the frequency is 1, so we update the maximum to 5 and add 5 times 1 to the total_sum, bringing it to 13. With the total_sum now at 13, we calculate the mean by dividing the total_sum by n. Here, 13 divided by 4 gives us 3.25. Next, we move on to find the median. Since the dataset size is even, the median positions are the middle two values, which correspond to indices 2 and 3. To locate the median, we traverse the count array while maintaining a cumulative count of elements. At index 2, the cumulative count is 1, which is less than the first median position, so we continue. At index 3, the cumulative count reaches 3, covering both the second and third positions. This means the median values are both 3. Averaging them gives a median of 3.0. Finally, the output for this dataset is 2.0, 5.0, 3.25, 3.0, 3.0, representing the minimum, maximum, mean, median, and mode in that order. Now let's consider a sparse dataset where the count array has only 2 non-zero values, at indices 2 and 6. Here, n, the total number of elements, is 2. We initialize our variables as before. At index 2, the frequency is 1, so we set both minimum and maximum to 2, add 2 to the total_sum, and update the mode to 2 since it has the highest frequency so far. At index 6, the frequency is also 1, so we adjust the maximum to 6 and add 6 to the total underscore sum, making it 8. The mode remains 2, as there's a tie, and we keep the smallest value as the mode. The mean is calculated as the total underscore sum divided by n, which is 8 divided by 2, giving us 4.0. To determine the median for this dataset, we again look at the middle positions. Since n is even, the median positions are the first and second values. As we traverse the count array, the cumulative count reaches 1 at index 2, which corresponds to the first median value. Continuing to index 6, the cumulative count becomes 2, covering the second median position. The median is therefore the average of 2 and 6, which is 4.0. The output for this dataset is 2.0, 6.0, 4.0, 4.0, 2.0, representing the minimum, maximum, mean, median, and mode respectively. Finally, let's examine a uniform distribution where every value from index 0 to 4 has a frequency of 1. Here, n is simply 5, the total number of elements. For the initialization, we begin with minimum, maximum, total underscore sum, mode, and max underscore frequency set appropriately. Each index contributes equally, so the minimum is 0, the maximum is 4, and the total underscore sum is the sum of all indices, which is 10. The mode is set to 0, as all values have the same frequency, and we select the smallest value in case of a tie. The mean is calculated as 10 divided by 5, yielding 2.0. For the median, the dataset size is odd, so the median position is the middle element, which corresponds to index 2. Thus, the median is 2. The output for this dataset is 0.0, 4.0, 2.0, 2.0, 0.0, giving the minimum, maximum, mean, median, and mode. In this solution, the time complexity is determined by the fixed size of the count array, which always contains 256 elements. Each operation that processes this array runs in constant time, O(1). For instance, calculating the total number of elements, n, involves summing up all values in the count array. Since the array size is fixed, the sum, count, operation takes O(256) time, which simplifies to O(1). Similarly, finding the minimum, maximum, mean, and mode involves iterating over the count array, performing operations like comparisons and arithmetic for each index. Again, this step involves 256 iterations, so its complexity is O(256), or O(1). When determining the median, another loop through the array calculates cumulative sums and compares them against the predefined median underscore positions. Despite the slightly different logic, this operation still involves only 256 iterations, making it O(1). By combining these steps, the solution achieves an overall time complexity of O(1), as every operation depends solely on the fixed size of the count array and not the actual size of the dataset it represents. Turning to space complexity, this solution is also highly efficient with a constant space complexity of O(1). The count array, which is the input, has a fixed size of 256 and does not require any additional memory overhead. It is processed directly without modification. The solution also uses a set of scalar variables, such as minimum, maximum, total underscore sum, mode, and max underscore frequency. These variables store intermediate results and require constant amounts of memory regardless of the dataset size. Additionally, there are small lists, like median underscore positions, which contain at most 2 elements. These minor structures also require constant space. Importantly, no other data structures, such as dynamically growing arrays or hash maps, are used, which ensures that the memory footprint does not increase with the size of the dataset. Together, these factors confirm that the solution's space complexity remains O(1). When comparing this optimized solution to a brute force approach, the efficiency gains become clear. A naive method might involve reconstructing the dataset explicitly from the count array, which would require iterating over the array and creating a list of all elements. This approach would result in a time complexity of O(n), where n is the total number of elements in the dataset. It would also require O(n) space to store the reconstructed dataset. In contrast, the current solution avoids this by directly working with the count array, leveraging its fixed size to achieve constant time and space complexities of O(1). This eliminates the need for dataset reconstruction and significantly reduces overhead. By processing the compressed representation of the data efficiently, the solution is ideal for handling large datasets. In summary, both the time and space complexities are 1, thanks to the fixed size of the count array and the elimination of unnecessary operations. This makes the solution exceptionally well suited for large-scale problems where efficiency is critical. Let's go over some common mistakes to watch out for when solving this problem. First, a frequent pitfall is mishandling the median, especially with even-sized datasets. Remember, you need to calculate the average of the two middle values, not just pick one arbitrarily. This can easily result in subtle off-by-one errors, particularly if you're not careful with array indexing. Another common issue arises in calculating the mode. The mode is the value that appears most frequently, but what happens if there's a tie? A common mistake is returning the first value with the maximum frequency without checking for other values that may share the same frequency. Handling ties properly is essential. You also need to think about edge cases. For instance, how does your solution behave with an empty dataset, or when all values in the dataset are identical? Ignoring these scenarios can lead to runtime errors or incorrect outputs. Lastly, inefficiencies can creep in if you recompute values like the sum or frequencies multiple times. For example, if you calculate the total sum for the mean repeatedly instead of reusing a pre-computed value, you're introducing unnecessary overhead. Always look for ways to streamline your computations. Another critical consideration is integer overflow. This is particularly relevant in languages like Java or C++ when working with large datasets containing extreme values. Overflow can occur when summing up large numbers or calculating the mean. To avoid this, use appropriate data types, such as long in Java, or apply modular arithmetic where necessary. From an interview perspective, efficiency is a key expectation. While a brute force approach might solve the problem, interviewers typically want to see optimized solutions with better time and space complexity. For instance, instead of making multiple passes over the count array to compute statistics, consider how you can calculate all required metrics in a single pass. Additionally, showing awareness of edge cases is crucial. Be prepared to explain how your solution handles scenarios like empty datasets or ties in mode calculation. Space optimization is another area to focus on, especially for large datasets. Discuss techniques like using in-place updates or maintaining running tallies instead of creating additional data structures. Finally, communication is vital. When presenting your solution, make sure to clearly explain the sequential steps you took to calculate metrics like the mean, median, and mode. This helps the interviewer follow your thought process and assess your problem-solving approach. Now let's connect this problem to some related challenges that you may encounter. For instance, LeetCode problem 1090, largest values from labels, focuses on optimizing values under constraints, which is conceptually similar to computing statistics efficiently. Another relevant problem is LeetCode 295, find median from datastream, which involves dynamically calculating the median as data is added or removed, a useful variation that builds on the concepts in this problem. LeetCode 451, sort characters by frequency, ties closely to mode calculation as it requires analyzing frequency distributions and sorting accordingly. Lastly, LeetCode 528, random pick with weight, introduces weighted values, which relate to the statistical computations you perform here. Exploring these problems can deepen your understanding of statistical techniques and their applications in different contexts. When considering alternative approaches, it's important to evaluate the trade-offs associated with each. A brute force approach, where you iterate over the dataset multiple times to compute each statistic, is straightforward but inefficient for large datasets due to its O(n) complexity per statistic. A more efficient method is the single-pass approach, where you compute all statistics in just one iteration of the count array. This reduces time complexity but requires careful bookkeeping, such as maintaining running values for the minimum, maximum, sum, and so on. If the dataset is dynamic, with values being added or removed over time, a heap-based approach is worth considering. Using a min heap and max heap enables efficient median calculation, though it comes at the cost of higher space complexity. Another option for median calculation is a sorting-based approach. While sorting the dataset simplifies the process, it introduces an O(n log n) complexity, which may be suboptimal for large datasets. Each method has its strengths and weaknesses, so selecting the right one depends on the problem's constraints and requirements. Great job completing this problem walkthrough. We reviewed an efficient approach to compute key statistical measures and discussed its practical applications. Remember, mastering problems like these strengthens your data analysis and algorithmic thinking. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!